Hello everyone, welcome back to my channel. Keep calm and love maths. This is part 4. I am going to start from the question that I have mentioned yesterday. So the question was, give examples of two relations such that one is an equivalence relation and the other is not. So the equivalence relation is it is a binary relation which satisfies all the three relations that are reflexive, symmetric, and transitive. Now we are taking an example which is defined as the relation R ordered pair A comma B such that modulus of A minus B is even, and this relation is defined on the set A, that is 1 2 3 4 5 is an equivalence relation. So I am taking this example, and now we have to verify whether this relation R is reflexive, symmetric, and transitive. If so, then the relation R will be equivalence. So let's proceed. In the set A, for any elements 1 2 3 4 5, we get an ordered pair A comma A, that is A is related to A, such that this element belongs to the relation R. Because we all know that for any element A belongs to capital A, we get modulus of A minus A, which is equal to 0, is even. We all know that 0 is even number. So the element A comma A belongs to R for all element A in the set A. Therefore, R is reflexive relation. Now for symmetricity, let us take two elements A and B belonging to the set capital A. Let us take the element ordered pair A comma B belongs to R. Then modulus of A minus B is even, because already we have taken this belonging to the relation R. Then obviously modulus of B minus A is even, because modulus of B minus A is nothing but modulus of minus B plus A, which is again modulus of A minus B, and we know this is even as we have taken already. Therefore, for any element A and B belongs to the set capital A and an ordered pair A comma B belonging to the relation R, it implies that there is another ordered pair BA belongs to R. Therefore, R is symmetric. Now for transitivity, let us take three elements A, B, C belongs to the set A. And then let us take two elements ordered pair A comma B and ordered pair B comma C belongs to the relation R. That is, modulus of A minus B is even, and modulus of B minus C is also even. But modulus of A minus B is even, it implies that the element A minus B is even. Similarly, modulus of B minus C is even, it implies B minus C is even. Now we have seen A minus B plus B minus C, that is sum of these two, is also even, and which is nothing but here minus B plus B cancels out, so A minus C is even. Now if A minus C is even, then obviously modulus of that part will be even. It implies ordered pair A comma C belongs to R. So for two elements AB and BC belongs to R, we finally got ordered pair AC belongs to R. Therefore, R is transitive. Since the relation satisfies all the three relations, that is symmetric, reflexive, and transitivity, therefore the relation R is an equivalence relation. So we have found an example of equivalence relation, which is, here it is, the relation R ordered pair AB such that modulus of A minus B is even. On the set A, 1, 2, 3, 4, 5 is an equivalence relation. So this is done. Now come to the next example, which should be not an equivalence relation. And here it is. Let us consider a binary relation on this set A, 1, 2, 3 in such a way that relation R contains the element 1, 1, 1, 2, 2, 3. So since 2 is not related to 2 and 3 is not related to 3, so R is not reflexive. How? In the whole set A, we have 3 elements, 1, 2 and 3. But in the relation R, we have only 3 elements, 1, 1, 1, 2 and 2, 3. But the element 2, 2 and 3, 3 are not containing in the relation R. Therefore, R is not reflexive. Again, since 1 related to 2 and 2 related to 3 does not imply the elements 2 related to 1 and 3 related to 2, therefore R is not symmetric, because according to symmetricity, if we have an element in the form 1, 2 belongs to R, then it should imply 2, 1 is also belonging to the relation R. Therefore, this is not implying an element 2, 1 in the relation R. Therefore, this R is not symmetric also. Similarly, for transitivity, if 1 related to 2 and 2 related to 3, we should have an element 1 related to 3. But here in this relation set, we have 1, 2 and 2, 3. But there is no any element in the form 1, 3. Therefore, R is not transitive also. So, this relation R on the set A is not an equivalence relation. So, মই এইখিতে এটা কথা ক'বলৈ মন কৰিম যে আমি যদি এটা equivalence relation বিচাৰিব লাগে, তেন্তে এইটো নহয় যে সেই ৰিলেশ্যনটো গোটেই তিনিওটাই satisfy নকৰিব লাগিব। সেই ৰিলেশ্যনটো only reflexive নহ'লেও হ'ব, only symmetric নহ'লেও হ'ব, only transitive নহ'লেও হ'ব, because according to definition of equivalence relation, it is a relation which satisfies all the three. But if we find a relation which is not reflexive only, then also this relation will be an example of non-equivalence relation. So I hope you are getting it. Now the next question number 5. In the set of integers Z, examine whether the following relations are equivalence relation or not. Number 1, R equal to ordered pair A, B such that A, B belongs to integer and A less than B. We have to check whether this relation is an equivalence relation or not. First of all, we all know what is Z. Z is the set of integers. Let us take two elements A and B belongs to Z, and let us take A less than B. Right? That means we have taken A less than B. It means that there is an ordered pair A, B belonging to this relation R. There is an element A, B belonging to R. But we cannot find B less than A for any integers. This is very obvious, right? Suppose if I say minus 1 is less than 7. Minus 1 is less than 7, right? But is it true to be written as like this? 7 less than minus 1? Is it right? No, definitely not. It is not true. It is false. Therefore, for any elements a and b belongs to z, if we find a less than b, we cannot find b less than a for the integers a and b belonging to z. Therefore, this relation is obviously not symmetric. So it is enough to show that R is not symmetric. Then we can finally conclude that this relation R will not be an example of equivalence relation, right? কিন্তু তোমালোকে ইচ্ছা কৰিলে ৰিলেশ্যনটো ট্ৰানজিটিভো নহয় আৰু ৰিলেশ্যনটো ৰিফ্লেক্সিভো নহয় এইটো দেখাই দিব পাৰা। কিন্তু আমি যদি পায়ে যাওঁ যে R is not symmetric, then আমি এইখিনিতে ষ্টপো কৰি দিব পাৰোঁ, বিকজ ইট ইজ ইনাফ টু শ্ব' ডেট দিছ ইজ নট এন এক্সাম্পল অফ not an example of equivalence relation. That means R will not be an example of equivalence relation, right? ইয়াত মই কেনেদৰে ৰিফ্লেক্সিভ নহয় সেইটো দেখাই দিছোঁ। Suppose we have an integer a. It is not true that a less than a. This is not true, right? Because if I say there is an integer, suppose 5, can we write 5 is less than 5? No, definitely not. But yes, we can say 5 may be less than or equal to 5, because here equal signs means 5 is equal to 5. But we cannot write 5 is less than 5. This is not true. This statement is not true. Therefore, we cannot get an element a comma a in R. So this element does not belong to R. Therefore, this is not reflexive also. Hence, we can finally conclude that R is not an equivalence relation. Now, number 2. Here, number 2 is R equal to ordered pair AB such that AB belongs to Z and A less than equal B. Let's see. Let us take two elements in the set of integers 5 and minus 9. Here minus 9 is less than equal 5. I can write in this way. I can write karon minus 9 to 5 koi horu hoy. Homan nohoy, no doubt, kintu horu hoy. Kintu etu jano hotto hobo 5 less than equal minus 9. 5 to minus 9 or equal nohoy. Aru 5 to minus 9 ko horu nohoy. So a statement to bhul hobo. That means in the set of integers, for this definition of relation, we cannot find symmetricity. So this relation R is not an equivalence relation. This relation R is not an equivalence relation. ভালকে চাই ল'ব পাৰা। আৰু কি দিয়া আছিল AB such that AB belongs to set of integers and A less than equal B. মই জাষ্ট symmetricity নহয় সেইটো দেখাইলোঁ আৰু সেইটো দেখুৱাটোৱেই ইনাফ হ'ব, বিকজ ইকুইভেলেন্স ৰিলেশ্যন নহ'বলৈ হ'লে তাৰে তিনিটা ৰিলেশ্যনৰ কোনোবা এটা ছেটিছফাই নকৰিলে ই ইকুইভেলেন্স ৰিলেশ্যন নহয়। চ' number 2 is not an example of equivalence relation. Number 3, R equal to ordered pair AB such that AB belongs to Z and A greater than B. Now we have to examine whether this R is an equivalence relation or not. So this is also very obvious. I think you can solve this very easily. Now the solution is for any elements A and B belongs to the set of integers. Suppose we take A greater than B. Can A greater than B imply B less than A? No, this cannot imply because if we take 0 is less than 10, this is true. 0 to 10 কৈ সৰু হয়। মই এই ষ্টেটমেণ্টটো যদি লৈ লওঁ, এতিয়া মই যদি লিখোঁ 10 less than 0, এই ষ্টেটমেণ্টটো শুদ্ধ হ'বনে? ডেফিনেটলি নহয়। 10 কেতিয়াও 0 কৈ সৰু হ'ব নোৱাৰে। চ' এই ৰিলেশ্যনটোৰ ক্ষেত্ৰতো মানে এই ডেফিনেশ্যনটোৰ ক্ষেত্ৰতো এ বি বিলংছ টু জেড এণ্ড এ গ্ৰেটাৰ দেন বি, এই ৰিলেশ্যনটো কেতিয়াও চিমেট্ৰিক হ'ব নোৱাৰে, ৰিফ্লেক্সিভ হ'ব নোৱাৰে আৰু ট্ৰেনজিটিভো হ'ব নোৱাৰে। গতিকে the relation are AB such that AB belongs to Z and A greater than B is not an equivalence relation. So let's come to the next question, that is for the relation are ordered pair AB such that AB belongs to Z and A minus B is divisible by 2. So let's first check reflexive. A minus B is divisible by 2. Now if we take an element A belongs to the set of integer Z, then A minus A equal to 0. All we know that A minus A equal to 0 and 0 is divisible by 2. Therefore we find an element A comma A belongs to R for all A belongs to integer. Therefore this relation is obviously reflexive. Now symmetricity. Let A minus B is divisible by 2. That means we have taken that the element A comma B belongs to R. That means A comma B belongs to R. Now B minus A. Now B minus A is nothing but the negative of this A minus B. B minus A equal to minus of A minus B. Since this is divisible by 2, so obviously minus of this also divisible by 2. Therefore B minus A is divisible by 2. And if B minus A is divisible by 2, then the element BA belongs to R. Then the element BA belongs to R. So if an element AB belongs to R, it implies that BA belongs to R. Therefore it is symmetric also. Next, transitivity. Let us take two elements. A minus B and B minus C are divisible by 2. We have taken these two elements which are divisible by 2. Now sum of these two is also divisible by 2. It is very obvious. And sum of these two equals A minus C because minus B plus B cancel out. Therefore A minus C is divisible by 2. And it also implies that element in the ordered pair AC belongs to R. Hence R is transitive. Since this relation R is reflexive, symmetric as well as transitive, therefore this relation is an example of equivalence relation. So I hope you are getting it well, right? So let's proceed to the next question, which is 5, not 6. So the question is, are AB such that AB belongs to set of integer Z and A square equal to B square. The question is, are AB such that AB belongs to the set of integers and A square equal to B square. So now we check. For any integer A belongs to Z, we can write it as A square equal to A square. We can write it. So the element A comma A belongs to this relation. Therefore R is reflexive. This is very obvious. Now for symmetricity, for any two elements A and B belonging to the set of integers, let us take A square equal to B square. That means ordered pair AB belongs to R. we get b square equal to a square, right? It is obvious because this is the rearrangement only. We have written it as b square equal to a square in place of a square equal to b square. This is all equal. Therefore, the element AB belonging to this relation R implies there is another element BA that also belongs to R. Therefore, R is symmetric. Now, transitivity. Let A, B, and C belongs to set of integers that then we suppose two elements ordered pair A, B and B, C belongs to R. These two ordered pairs belong to the relation R. Then according to the definition of question, A square equal to B square and B square equal to C square. Now we see combining these two, we get A square equal to C square. According to the definition, ordered pair A, C belongs to R. Therefore, for any two elements A, B and B, C belonging to the relation R, we finally get an element AC belongs to R. Therefore, R is transitive. Since R is reflexive, symmetric and transitive, therefore R is an equivalence relation. So this question is done. Now come to the next question. Here it is. A binary relation R in the set A containing 2, 3, 4, 5, 6 is defined by x related to y, where modulus of x minus y is divisible by 3. The question is R an equivalence relation? Here we are given that a binary relation R in the set A containing the elements 2, 3, 4, 5, 6, and it is defined in the way modulus of x minus y is divisible by 3. Is R an equivalence relation? Let's say R goes from A to A. R goes from A to A itself. For reflexivity, let us take the element 2 in this set. 2 belongs to A. Now modulus of 2 minus 2, which is always equal to 0, and 0 is divisible by 3, right? Similarly, for the other elements in the set A also this condition is satisfied. That means 3 minus 3 equal to 0, and it is divisible by 3, and so on. Therefore, R is reflexive. Now, to check symmetric, let us take two elements 2 and 5 belongs to A. Now, modulus of 2 minus 5 is equal to modulus of minus 3, and modulus of minus 3 means plus 3, and 3 is divisible by 3. All we know, 3 is divisible by 3. And also modulus of 5 minus 2 is 3, and 3 is divisible by 3. So for an element 2, 5 belongs to relation R, we get another element 5, 2 belongs to R. Therefore, R is symmetric. Now for transitivity. Let us take two elements 2, 5 and 5, 2 belongs to the relation R. Here it is. Now, if 2, 5 belongs to R, then modulus of 2 minus 5 is divisible by 3. Similarly, if 5, 2 belongs to R, then modulus of 5 minus 2 is divisible by 3. Now, 2 minus 5 plus 5 minus 2 is divisible by 3 because these two are separately divisible by 3. Therefore, sum of these two is also divisible by 3. Now, sum of these two is nothing but 2 minus 5 plus 5 minus 2. Minus 5 plus 5 cancels out the remaining. 2 minus 2, and 2 minus 2 is 0. It is nothing but this is 0. All we know, 0 is divisible by any number, 0 is divisible by 3 here. Therefore, for taking two elements 2, 5 and 5, 2 belonging to the relation R, we get another element 2, 2 belongs to R. 2, 5 and 5, 2 implies 2, 2 belongs to R. Therefore, R is transitive. Therefore, R is transitive. Since R is reflexive, symmetric and transitive, since this is symmetric, reflexive and transitive, hence R is an equivalence relation. So this is also done. So in this class, in this whole class, I have solved some problems related to symmetricity, reflexivity and transitivity, and also equivalence relation. So I think you are getting it. If you are not understanding, then please do write in the comment section so that I can help you. It's all about this class. So keep watching and also subscribe to my channel to stay updated. Bye bye. Thank you.